So both the recording and PDF notes will be made available to you. Okay. So this is Newton's first law, which is the law of inertia. It defines this property of any object. Anything that has mass has a property of inertia. If it is a very light object like an electron or a proton or a subatomic particle, it has comparatively very less inertia. So very little amount of force is needed to change its uniform motion. But nonetheless, as long as it has mass, it's going to possess inertia. If it's a much heavier object like a building or something, or even the earth, it has a very, very large amount of inertia. So we require very large amount of force to change its state from either rest or uniform motion. But large or small, it doesn't matter. Each and everything has the property of inertia. Thereby, it wants to continue in its state of rest until and unless there is external force acting on it. So just to make this clear, we understand there are two different types of inertia. Inertia of rest. So if a body is at rest, it will continue to be at rest until and unless some external force acts on it. So let's say we have got a block at rest on a smooth surface. So smooth means there's no friction. So there's no way this is going to move. It will not move until and unless some external force is applied on it. So now if we, for example, apply some external force, it doesn't matter what the direction of the external force. It could be horizontal, it could be obliquely like this, whatever be the case, but then it will start moving. Then the motion starts. So its state of rest changes. But until and unless that external force acts, there is no change in its state of rest. Okay. Similarly, there is also inertia of motion. So let's say we have already applied a force on a body for some time, and thereby it's brought into a state of motion. So this body is moving at uniform velocity on a frictionless surface. So in this chapter, all the surfaces we'll be dealing with, they are smooth or frictionless surfaces. So they're moving, if it's moving with a velocity v0, it will continue until and unless some external force acts on it. So it will continue moving uniformly at velocity v0 until and unless some external force acts on it. So that is the inertia of a moving object. So you can say it's inertia of motion. For example, while it is moving, now if we start applying some force in this direction, then it will start accelerating. Now its speed will increase. But on the other hand, if we were to apply the force in this direction, then its speed would start to decrease. But anyhow, until and unless there is some external force acting, neither the direction nor the magnitude of velocity will change. Okay, so when we say that uniform motion it means that the velocity v is constant. So if net force equals to 0, okay, then neither the direction nor the magnitude of the velocity v will change. Even to change the direction of a moving body, we need to apply some force. So for example, if you see an object which is moving on a smooth horizontal surface like this is not vertical. Okay, so this is on a smooth surface. basically like this. Imagine on a smooth tabletop, we have this object moving with a velocity v0. So it will have a tendency to continue in this direction. So if I want the velocity vector to turn direction, I'll have to apply a force. So if I apply a force like this, for example, now its motion will tend to turn like this because of the application of the force. So the direction will change only if external force acts on it. In the above two examples, the magnitude was changing because we are applying the force along the motion. So this is moving at v0 and we apply the force in this way. Now the magnitude of v will change. Only when some force is applied. So this is basically what we mean by Newton's first law, especially the inertia of motion part, that if something is already moving with a velocity vector, then it has a tendency to keep that velocity vector constant. Until and unless some external force acts on it, that velocity vector is not going to change. So whether we want to change the magnitude of the velocity vector or we want to change the direction, some external force will have to be applied. Otherwise, it's not going to change. And that is the property of inertia. Why it has a tendency not to change? Because the body has that property of inertia, which is measured by its mass. So the larger the mass of the body, the more inertia it has. So, comparatively, if you take two bodies moving in the same state with the same velocity, which one will require more amount of force to change its momentum or to change its velocity? The one having more inertia. So that is the one having more mass. So hence we measure the property of inertia by the mass of the body. And as you know, the unit of mass, the standard unit of mass is kilograms in SI system. Okay. So the first law also introduces the concept, apart from introducing the concept of inertia, it brings into play this property, this physical property of anything which is mass, okay, which has the standard unit of kilograms. Now that brings us to the second law. Now the statement of the second law actually involves a new, maybe something which is a new term for us, which is momentum. So Newton's second law states that the net external force acting on a body equals to the rate of change of its momentum. So now, first of all, we'll understand what is momentum. Momentum is a vector quantity denoted with the symbol P, which is mass into instantaneous velocity. So M is mass of the body that we're discussing about, and V is its velocity. So then P becomes the instantaneous momentum. So according to the above statement, the Newton's second law in mathematical form becomes that the net external force equals to the rate of change of momentum. This is the mathematical form of it. This is the net external force. Okay. So differentiation of momentum with respect to time, dp by dt. This is differentiation or instantaneous rate of change of linear momentum p with respect to time. Yeah, so Khushi, I will just answer your question in a moment. Okay, F is equal to ma is another way of expressing it, but that is a conditional statement. Okay, but the proper definition of Newton's second law is actually that net force is equal to dp by dt, that is rate of change of linear momentum. Okay, that reduces to net force is equal to mass into acceleration in a special circumstances, and what that is also I'll discuss in a moment. Okay. So especially those of you who are studying Newton's laws fresh from the start, you can just make a note of this concept over here. Firstly, the definition of linear momentum. So P is momentum, or it is also called linear momentum. They mean one and the same thing, mass into velocity. So momentum or linear momentum. Okay. You can see momentum is measured in kilogram meter per second. Or we can also express it in Newton second. And force is measured in newtons, where 1 Newton is equivalent to 1 kilogram meter per second square. I'm writing all the SI units over here. Okay, this is the standard international units. So as you have rightly stated, Khushi, that F is equal to ma is one way of writing Newton's second law, but that will actually come from this broader definition. Okay, and it will come in a special circumstance that mass should be constant. So when we are talking about rigid bodies or solid objects, that is always the case, that mass is constant. However, Newton's second law is not just limited to rigid bodies. We can also apply Newton's second law to a system like, let's say, a conveyor belt on which mass is constantly being added. So the mass is not constant, it's increasing. Or like we can apply it to a tanker which is leaking and therefore its mass is decreasing. So in those cases, we will see that F is equal to ma will not be the correct way of expressing Newton's second law. We will have to incorporate a little bit more of calculus into that. Okay. That is why the proper definition of Newton's second law is not F is equal to ma. It is a special case of Newton's second law. The proper definition is that it is net force is equal to rate of change of momentum.
Sir, sorry.
Yeah, tell me बेटा. No, it's fine. Any doubt?
सर मेरी बहन मस्ती कर रही है, वो उसने वो डॉट लगाया आपके पीडीएफ पे.
It's okay, it doesn't matter. I have disabled the annotation, so it doesn't matter. It's fine.
Thank you, sir.
Okay, so hope this definition is clear. First of all, momentum concept is clear, and then the definition of Newton's second law. This statement converts to this formula. Okay, now here we must understand what is meant by net external force. So net external force is the vector sum of all forces acting on the given body. So suppose we have n number of forces acting, then we have to use vector algebra to add all of these, F1 plus F2 plus like this one. This is, these are n forces acting on the body. So we will typically use component algebra, that I cap J cap notation that you are used to. We'll typically use component notation. Sometimes we might also use the geometrical notation like parallelogram law or triangle law or polygon law. But generally we don't do that in this chapter when we are calculating net force. So we need to calculate the sum of forces. So most often the common method that we use is the component algebra method. So vector summation is something that becomes important here. That is where your application of vectors from previous chapter will come into this application. Now, the very important thing, that because momentum is equal to mass into velocity, so rate of change of momentum, which is the right hand side of this equation, is differentiation operator applied to mv. Okay. Now, this is where we will see two categories of systems. Okay. One is if m is the mass of a rigid body, so it's got a fixed mass. which is basically what we'll apply in this chapter. Newton's laws of motion, we're always talking about rigid bodies of fixed mass. Okay. So then in this case, rate of change of momentum में क्या हो जाएगा? When we take the differentiation operator inside, m is a constant, so it just comes out. So it becomes m into dv by dt. And dv by dt, kinematics, you would have seen the basics, it is mass into acceleration. So the left, the right hand side of the equation, rate of change of momentum becomes ma. Okay. But on the other hand, we can also have a system where m is variable. So this is called a variable mass system. Now, initially, it might seem odd to us, how can mass be vary? But remember that Newton's laws, we are not limiting ourselves just to applying it to an object or a rigid body. We can apply it to a system also, like a conveyor belt or a tanker or a rocket or something like that. Okay. So if mass is variable, example of that is a conveyor belt. So mass being added continuously. So mass is increasing in this case, suppose. Of course, you might say that in typical conveyor belts, kahin se mass add ho raha hai, so at some other point, mass must be getting removed also, because it's just used to transport mass from one point to another. But I'm just saying, let's take a special case where we are only loading the conveyor belt. We are not unloading it. Now, so you've all seen those baggage conveyor belts in airports. So at the time when they are being loaded from the aircraft end, and before the passengers start to unload their boxes, so mass is only being added at that time. So the mass of that whole system is increasing. So that is an example of variable mass system. Siddharth, I'm just reading your doubt. M variable will store a constant only, so at last it will be 0. Didn't really understand your doubt, beta. Siddharth, can you can unmute
Sir, that
yourself?
m that you are telling that it is a variable mass system, that will
Yeah.
also store a number only, no? So if you will apply differentiation operator, it will be 0 only at last, because differentiation of constant is 0.
But I'll explain one thing. No, it's a variable quantity. So it's not a constant. Okay, so for example, if I have a conveyor belt, okay, in which I'm adding from here, I'm let's say adding sand. Okay, now if I'm adding sand at the rate of let's say 5 grams per second, okay, and at t equal to 0, the mass of sand was 0. So at some general time t, what will be the mass of sand? It will be the rate multiplied by time. So it's a variable quantity, no, beta. It's 5t in grams. You understanding your point, no?
Yes, sir.
So is the rate of change 0? No. The rate of change is a non-zero quantity. Okay.
Okay,
Of course, every variable quantity has an instantaneous value. But see, when we calculate the rate of change, we don't take that instantaneous value. I'll just give you an example. Suppose I ask you y is equal to x square. I say find dy by dx at x equal to 2. So I don't substitute x equal to 2 first and then calculate dy by dx of 2 square. No, I don't do that, because that will give me 0, but that's wrong. What I do is I calculate dy by dx of x square. So that is 2x. Okay. And then I say that, okay, dy by dx, when the value of x is equal to 2, is nothing but 2x at the point x equal to 2. So it is 4. So 4 is the slope of the tangent of that curve y is equal to x square at the point 2. So I think what you're asking is related to this somehow, right? You understood, Peter?
Yes, sir.
So that's why. Okay. So that's one example of variable mass system. Another example is you could have a situation like a leaking tank. Okay. So mass is decreasing. Okay. So let's say we have a tank on a smooth surface, and in that we have some mass of water. Okay. But somewhere there's a leakage, so mass is reducing. Okay. And then we are pushing it with some external force, and we want to apply Newton's second law. But here we will see that mass is a decreasing function of time. So it is definitely not constant. And here also you can see that mass is increasing. So definitely it is not constant. So these are just two examples. A lot of other examples we'll also be seeing. But typically variable mass system, I'm just giving you as an understanding point over here. We'll be dealing with variable mass systems in a later chapter called system of particles. Okay. But here you should just know how to deal with it. Okay. So in this case, variable mass system, when I apply Newton's second law, I'll just minimize it later. So when we apply Newton's second law, rate of change of momentum, understand that m is also variable. And of course, we are assuming that velocity is changing. So v is also variable. Oh, Rishita, that's a very interesting point. I'm coming to that. That has to do with relativity, actually. Relativity and the concept of dynamic mass. If you've heard of Einstein's theory of special relativity, right? So we'll
Yes,
discuss
sir.
about that. Yeah, so that has to do with that, actually. Okay, so that's a very interesting point in itself.
Okay, sir.
I'll come to that. So when I'm doing the differentiation here, I will use product rule. So it is dm by dt into v plus m into dv by dt. So it is the rate of change of mass into the instantaneous velocity plus instantaneous mass into acceleration at that point of time. That will be the net force. And you can see that this second equation that we've written is like a generalization. If you reduce it to a constant mass system, then your dm by dt is just zero. So just put dm by dt zero in this equation, and you'll see you'll come to what we have on the left hand side, which is that net force is equal to m into a. So you can just understand that this is the case basically. If dm by dt is zero, then automatically we are talking about a constant mass or fixed mass. So it has to reduce to that definition, that net force is equal to mass into acceleration. Okay, so just do a quick roundup of this part. Jot down some of the equations if you like, or you can make the notes, but make sure you understand that there are these two separate cases, variable mass system and fixed mass system. So in fixed mass case, Newton's second law becomes like this. In variable mass case, it is a little bit more complicated. This we'll be doing in another chapter. Okay, we will learn this. We will apply this rather in later chapter called system of particles. Whereas this is what we'll be applying right now. This will be applied in Newton's laws of motion chapter. Yes, exactly, Siddharth. That is the correct point. That F is equal to ma is applicable only when the mass is constant. Okay, so now I'm just, Rishita, since you've asked this very interesting question, normally we don't discuss this as part of mechanics because it's part of a branch of physics called relativity or relativistic mechanics, but we'll discuss it here anyhow. It's a very interesting thing. So just as a separate note, okay, this is not in syllabus for us here. It's not in syllabus, but still, no problem. It doesn't matter. Everything is part of your knowledge in physics, whether it is in syllabus or out of syllabus, it doesn't matter. Okay. So we have something called relativistic mass. This is a concept explained by Albert Einstein. All of you must have heard about Einstein, one of the greatest minds in physics ever. In what is called his special theory of relativity. So what, as it turns out, that when we have subatomic particles or extremely tiny particles, or even subnuclear particles, like, for example, electrons, protons, neutrinos, etc. So when subatomic particles move at extremely high speed, so that extremely high speed is such that its order of magnitude is same as the order of magnitude of c, where c is speed of light, which I'm sure and most of you know is an extremely large amount of speed. It is approximately 3 lakh kilometers per second, or 3 into 10 raised by 8 meters per second. So when such particles move at speeds comparable to the speed of light, comparable to c, then they become heavy. They become heavier, and therefore they possess very large energy. That also brings into play the mass energy relation, which you might have heard of, E is equal to mc square. So there are two equations that become important over here, that m is given by the formula m naught upon square root of 1 minus v square by c square. And the other equation is that E is equal to mc square. So here the quantity m, it is called the dynamic mass. Okay, that is, it is the mass while in motion at speed v, and c is of course speed of light in vacuum or air, whatever. Okay, and m naught is what we call the rest mass. That is the mass measured when the body, or in this case it's more applicable to particle, is at rest. So now this is like very counterintuitive, you know, Rishita, it's something that we don't expect. Okay, we expect mass to be a very fundamental property. So how can mass depend on motion? And it was very shocking when it was discovered, right? You've heard the story, like, of relativity. It was not something that came easily to be accepted at the time when it was proposed by Albert Einstein. But of course, a lot of experiments in particle physics also backed up the theory. So now you can see, for example, if I have something moving at, let's say, 1000 kilometers per hour, or let's make this easier to calculate. Let's say it's traveling at not even 1000, but 18,000 kilometers per hour. So it's a huge amount of speed. Now, Like in our everyday sense, you can see that 18,000 kilometers per hour is a very massive amount of speed. We don't really see that very commonly. But let's see in meters per second how much this is. So that's 5,000 meters per second. Following so far, Ishita beta?
Yes, sir.
So now let's see what will be the relation between its. So suppose its rest mass is 1 kg, and we want to calculate its dynamic mass. So we'll see its dynamic mass is the rest mass upon root of 1 minus v square by c square. So it is still 1 kg divided by square root of, now see what this number is. It is 1 minus 5 into 10 raised power 3 divided by 3 into 10 raised power 8 square now. So it's like this. It's 1 kg upon square root of 1 minus 1.67 or 5 by 3 into 10 raised power minus 5 ka whole square. So you can imagine this number is very small now.
Yes, sir.
You can see that v square by c square is extremely small compared to 1. So we can take square root of 1 minus v square by c square as 1 only. No? So the dynamic mass is equal to the rest mass. So this is why the concept of dynamic mass doesn't come into play in our regular everyday physics, which we call the classical physics or classical mechanics. So we are applying that to situations like, moving vehicles or machines, okay, or simple Newton's laws type of experiments, like you're applying this to a set of particles which are colliding with each other on a carom board or things like that. So what we call Newtonian mechanics or classical mechanics, in that kind of situation, we don't come across this situation at all. There is no measurable difference between dynamic mass and rest mass, even if the velocity is very high by that comparison. Like 18,000 kilometers per hour is a very high velocity for classical physics. But then in the world of particle physics, it's not a high velocity. It's in fact a very low velocity. In the world of particle physics, to do some significant experiment, like you do, when you make subatomic particles collide in a particle accelerator. Right, Ishita, you would have heard the term of particle accelerator.
Yes, sir.
They are called cyclotrons or particle accelerators. So there, the speed of a particle, of course, we are talking about very light particles like electrons or neutrinos or things like that, is much, much higher. It's not 10 raised power 3 meters per second. It is of the order of 10 raised power 7 meters per second because it's approaching the speed of light. So then you will see that that denominator is no longer negligible. It becomes significant. So that is why what happens is that this concept of relativistic mass, it comes into practice actually only in the case of particle physics, where particles are moving at what we call relativistic velocities. Relativistic velocities means the velocity is not equal to speed of light, but comparable to speed of light. But in classical physics, we don't really encounter anything moving that fast. So the dynamic mass does not come into play. However, if something was moving that fast, it would become extremely heavy. So that 1 kg block, if it was moving at, let's say, half the speed of light, you can see its mass would become very large. It would become m0 divided by square root of 1 minus 1 by 4 now. So it would be significantly larger than 1 kg. Okay, you're understanding the point, Rishita?
Yes, sir. Understood. Thank you.
Okay. So for example, suppose we have an example from particle physics. A particle physics experiment. In that, what is happening, that an electron which has a rest mass, which I'll just denote by ME because it's a very painful term, 9.1 into 10 raised power minus 31 kg. But that electron is moving at, let's say, very close to speed of light. It's moving at 0.998 times c. So it is moving at 99.8%, you can say, the speed of light. Then what will its dynamic mass become? So now you can see it's significantly how much heavier it will become. It will become 1 minus v square by c square, whole thing to the power half. So when you do this, this term will be 1 minus 0.998 square, and this whole thing to the power half. Anything simple here, I'll do this by calculator. Okay. So first of all, 0.998 square We'll give you a term which is even smaller. It will be like 0.999 something, if I'm not mistaken.
.996004.
Something like that, no? Just a second. Yeah, so this will become like 1 minus something like this now.
Sir, 6004.
9996004, no? So suppose I approximate it to fourth place of decimal, it's like this only, right? So this is ME upon 0.0004 to the power half. Okay. So it's ME upon 0.02, correct? So you can see 0.02 is how much? It is 2 by 100 now. So it's 50 times ME. You can see that mass, that electron will appear to be 50 times its mass when it's traveling at that kind of speed. So this becomes very, very significant in the world of particle physics, because it is possible to accelerate an electron to that kind of speed. But it's not, for example, possible to accelerate even a carom coin to anything close to speed of light. Okay, even a few thousand kilometers per hour will be nearly impossible for us in classical physics experiments. So that is why this concept of dynamic mass and relativistic mass does not come into our analysis in Newtonian physics or in classical physics. This is what we are studying over here. But yes, later when you will be studying particle physics, especially those of you who will take branches of engineering which have a lot of core physics in them in the early part, you will come across relativity. In fact, all your BTech courses first year has a core physics portion also, and that contains relativity, special theory of relativity. Even though special theory of relativity is not there in your 10+2 syllabus or JEE syllabus or NEET syllabus for that matter. Medical students, you will not be studying this mostly at all. But engineering students in your first semester, you will be studying about relativity. Okay, so this is just something moving aside from our regular topic, but something very interesting, and you might have heard of it before. So in case you're wondering about it, this is how it works. Okay, so both the examples were clear.
Yes, sir,
Okay.
clear.
Okay, very good. Okay, so now coming back to our Newton's second law. So let's quickly look at some examples of second law before we come to third law and its explanation. So from this point onwards, all examples we'll be thinking of will be examples where the mass is fixed. Okay. So let us say we have this situation now. We have this smooth surface, and on that we have placed a block like this. Now the mass of the block is 10 kilograms. And now let's say what I'm doing is I'm applying two forces on it. One force I'm applying like this. I'm applying it at 37 degrees, and the magnitude of this force F1 suppose is 50 newtons. Okay. And from the other side, I'm applying another force, but that's in this direction. It's horizontal and backwards. And that force has a magnitude of, let's say, 20 newtons. The block's mass is 10 kg. We'll take acceleration due to gravity as 10 meters per second square. So first of all, what we want to do is we want to show in a vector diagram all forces acting on the above block. Then by using Newton's second law, we want to find its acceleration both in magnitude and direction. And then suppose we also want to add one part that it starts from rest at time t equal to 0. So find its velocity and displacement after 2 seconds. At t equal to 2 seconds, what is the velocity? So you're applying these forces, F1 and F2 are acting continuously. They're constant forces. They're continuously applied on the block. So just try this out. People will discuss more about this. So those of you who have done more lectures of Newton's laws earlier, you'll be familiar with the concept of free body diagram, and you can apply that also. But for those of you, this is the first lecture, you don't need to do anything. Just follow the language of the question, the hint given in the question, that make a vector diagram to first of all show all the forces acting on the above block. And once you've shown all the forces, then you can apply Newton's second law, that net force is equal to mass into acceleration, because mass is constant over here. It's a block of fixed mass. So from that we'll be able to get that. Yes.
Vector diagram is the free body diagram itself, right?
Yes, basically FBD is another way of saying vector diagram, but specifically applied to forces.
Okay, sir.
You can apply vector diagram to any type of vectors like velocities, momenta, electric field, like that. But when we apply it to forces, we particularly call it a free body diagram.
Okay, sir.
Okay, so anybody has got the answer here? See one person's message. Yes, Rishita, very good. It's correct. So you'll see your net force will actually become 20 meters per second square along the positive x direction. Very good. Okay. So I'm going to just start as a hint for all of you, those who are starting out the question, with the first part by just showing what all forces are acting on that body. So I'll show that body in much smaller size. Okay. And we have the two so-called, external forces because they are applied by some kind of external agents. So we have these two forces which are like this. So this is F1. This is at an angle of theta equal to 37 degrees. This has a magnitude of 50 newtons. This is F2. It has a magnitude of 20 newtons. But apart from this, there are two other forces which are acting on the body. One is the gravitational force with which the earth is putting it. So that is the weight. And that will have a magnitude of mg. So m is given to us as 10 and g is 10. So this is 100 newtons. Okay. And then the ground will be pushing it up. Force, which is called the normal reaction force. So we'll be discussing in more detail about normal reaction force, but it's the force applied by the ground, by the floor. So this is the pushing force applied by the floor on the block. So what happens is, the floor is applying a sort of pressure into area kind of force like this at every point. So that vector sum, that net force is what we call the normal reaction force. And as a result of all these forces, the block will have an acceleration in this direction. Have an acceleration like this, which we want to calculate. Yes, Rishita, very good. That's correct. Okay, so this is the first part. Now for the second part, what I need to do is I need to calculate the net force. So I'm doing it from the very basics over here. Net force is the vector sum of F1, F2, gravitational force and normal reaction. And that net force will become equal to mass into acceleration. So to be able to do this vector algebra, I'll need to write the forces in. So next step, what I'll do is I have to resolve the forces in component form. And solve. So to resolve in component form, I'll take this as my x-axis, this as my y-axis. Horizontal. I won't need the z-axis because it's a two-dimensional situation here. Okay, so I'm just writing all the forces in resolved form first of all. F1 will be F1 cos theta I cap plus F1 sin theta j cap. So when I calculate it, F1 will have, just substitute the values and you'll see this will be 40 I cap plus 30 j cap in newtons, because cos 37 is 4 by 5. Sin 37
by
is
5.
3. Okay. Similarly, F2 in component form, we will simply write as minus 20 I cap in newtons. And mg we write as minus 100 j cap in newtons. And normal reaction is the unknown force. It is some n j cap. So it's an unknown force. The magnitude we are writing as n, but the direction is only known as j cap. So these things which you have written in component form for the four forces, now they need to be substituted in the statement of Newton's second law. So that will not only give us the acceleration, it will also give us the unknown quantity, which is
Normal reaction.
the normal reaction. Very good. Okay. So we'll be able to also calculate the normal reaction. This also we can calculate. Okay, so this process is actually what this chapter is all about. Newton's laws. Almost everything we are trying to achieve this idea only, that we want to solve net force is equal to mass into acceleration for a body of fixed mass. Of course, the systems will get more complicated. There'll be threads, pulleys, and all these things added. But at the end of the day, every time we'll have to reduce it to something like this, a diagram like this, and solve.
Oh,
Yes.
like in the first part, like how did you say the direction of acceleration?
Because see, it's on a floor, na? It's on a smooth floor. So the floor is supporting it. Na? The floor is not allowing it to move vertically. You understanding? Na?
Yes, sir.
So now you can see, अच्छा, acceleration right के तरफ है कि left के तरफ है? That you're asking.
नहीं सर, like जब resolve किया तो ऊपर की तरफ भी like force आ रहा है ना?
नहीं, but see, is it logical? You have kept a heavy block on the ground, okay, and the weight of that block only is 100 newtons, whereas F1's magnitude is how much? 50 newtons only. Plus F1
Yes,
is acting.
sir.
So is there any way
Yes,
it's going
sir.
to get off from the ground? No, na? Okay.
No, sir.
But suppose F1 was something like 200 newtons here, then I can't be sure. Maybe it's getting lifted from the ground. So then I have to solve this and see if N is coming out to be a positive quantity or not. If the normal reaction N is coming out to be a negative quantity, for example, by solving this FPD, then it's logically not possible. Na?
Yes, sir.
The ground
Okay, sir.
down. Okay, so N can't become negative. So that means it will remain in contact with the ground and move horizontally only if I get a non-zero value of N. I mean a positive value of N. And you can see here that has to happen because mg is 100 Newton and F1 is only 50 Newton. So there's no way you're going to get a non-positive value of N.
Yes, sir.
So what should be the value of n then be?
So that is what we have to solve for now. Na? अभी ये equation को हम solve करेंगे ना. We'll substitute all these values. We'll substitute them here. And when we substitute and we solve, we'll solve to find two things: the magnitude of the acceleration and the normal reaction. Both the things we'll get. Okay. So what I can do is I can directly vector substitute these values, or I can write in component form, which is easier. But let me start with the vector substitution. So F1 is how much? It is 40 I cap, okay, plus 30 J cap. F2 is how much? It's minus 20 I cap. Okay. Mg is how much? It is minus 100 J cap. And N is some unknown quantity N, but J cap. So this should be equal to mass into acceleration. So the mass was 10 kg, I think.
10 kg.
Yes. 10 A, but the direction I can already see of the acceleration is what? I cap. So this is there because acceleration is along the x-axis. That I'm sure of from the beginning. Okay. So acceleration, the x component only is A and y component is C. Okay. Same way here, I can see that normal reaction is a vertical force. Okay. So now if I just write on the left hand side, it is 40 minus 20 I cap plus minus minus 100.
Minus 70.
Yeah, plus 30. Yeah, so 30 minus 100. That's correct. Minus 70. So 30 minus 100 plus n J cap. And on this side, it is how much? It is 10A I cap. So when we equate two vectors, their individual components will be equal. So 20 I cap plus n minus 70 J cap should be equal to what? 10A I cap. And the fact that J cap term is not there, that means it's 0 J cap. No? So when we are equating the two vectors, the x components are equated. That is the first equation, and the y components are equated. So n minus 70 is 0. That's the second. So this is showing me that the acceleration is 20 newtons divided by 10 kg or 2 meters per second square. And this is showing me that the normal reaction is 17 newtons.
70.
Okay. Now this I've still written in a bit of a complicated way because I've involved I cap and J cap. From this point onwards, we'll be directly writing it in component form. So we'll divide that equation into two components, X component and Y component, and we'll just write those two equations separately. Instead of writing in vector form I cap, J cap notation, we write it in components of vector notation. But anyhow, you can see this is how we apply the vector method for solving a situation involving Newton's second law, that the sum of many forces, in this case 4 forces, that is the left hand side, the net force, and right hand side, that is equal to mass into acceleration. Okay, so Siddharth, hope you have understood the answer to your question. How we know it's moving along the positive X direction? Because we can see that F1's X component is how much? Plus 40. And F2 is minus 20 along the X axis. No? So obviously F1 cos theta is dominating over F2. So another way of doing the same question is that instead of writing everything in I cap, J cap notation, the resolution of vectors type of method. So what we do is we start with our vector diagram, which we had earlier. Okay. But instead of converting that into I cap, J cap notation, I'm going to directly resolve the forces along the X and Y axis. So here we have F1, we have F2. This is 50 newtons at theta equal to 37. This is 20 newtons. Okay, then we had our weight. So if I try to draw accurately, this is a much longer vector. Okay, and we had a normal reaction. So also be comparatively quite a long vector. But the direction is upwards. So if you don't know the magnitude of, and the acceleration is in this direction. So next what I do is I resolve along X and Y axis, taking this as my X axis and this as my Y axis. So when I do that, this diagram gets somewhat converted. This diagram gets converted like this. You see, only one of the forces needs to be resolved here, and that is F1. So F1 के components क्या हो जाएंगे यहाँ पे? This will be F1 cos theta. That you can see will be 40, and y component of F1 will be F1 sin theta. That will become 30. And rest of the things are already resolved, so I don't need to do anything much. I'll just leave them the way they are. N is like this, then there is mg equal to 100 like this, and there is F2 like this, which is 20. So now in this diagram, straight away I can see that direction of acceleration is like this. Why I know it's like this? Because this is dominating over this. Okay, so Siddharth, you understood this point?
Yes, sir.
Okay, so now what we'll do is, instead of writing Newton's second law in vector notation, that is net force is equal to mass into acceleration, this equation only will divide into components. Along the x-axis or x component, we'll say that summation of forces along the x-axis is mass into x component of acceleration. So what all forces are acting along the x-axis? There is F1 cos theta, and there is minus F2 because it's along the negative x-axis, and the acceleration is this. So this is my equation 1. And similarly, along the y-axis, summation of forces along the y-axis should be mass into y component of acceleration. So forces are n plus F1 sine theta minus mg, but the acceleration is 0. The y component of acceleration is 0, and the x component of acceleration is what we want to find out here. So equation 1 and 2. So from equation 1, you can see we are getting 40 minus 20 is equal to 10a. So we're getting a is equal to 2 meters per second square. Okay, and from equation 2, we are getting n plus 30 minus 100 is equal to 0. So getting the normal reaction as 70 meters, 70 newtons. So this is another way of achieving that same result. And it's a little bit simpler because we don't have to use I cap, J cap and all that. We just straight away from the vector diagram itself, we are resolving the forces into x and y components. And we are able to divide this vector equation F net is equal to ma into two simple scalar equations, one along the x-axis and one along the y-axis. So this is going to be our regular method of solving Newton's second law in given problems. Okay, and this method is actually called the free body diagram method. We'll discuss a little bit more about it in detail. Okay. So almost every problem will be using this as part of the solution. That draw the body, show all the forces acting on it in a vector diagram, then resolve the forces into x and y components, and then finally write your F is equal to ma in component form. So F is equal to ma along the x-axis, again F is equal to ma along the y-axis, and then solve the equations that you're getting. You'll always get linear equations. There will be no quadratic or cubic terms or anything. So ultimately the solving is like solving of simultaneous equations, basically. Something like that will happen. So maths stepwise, it's a pretty easy chapter. The only technicality actually is the resolution of forces. Okay, so this is in effect, actually, this method is called the free body diagram method. So we'll come back to this in some time. In short, we call it FBD, or solving Newton's second law. This is like our, bread and butter or dal chawal in this chapter. Every other problem we need to, as part of the solution, we need to make either one or two or whatever number of objects there are. We need to make their free body diagrams. Okay. So before we come back to more examples and applications, let's quickly discuss Newton's third law. And through that, we will understand some things like normal reaction force, etc. So Newton's third law is called the action-reaction principle. In a sense, it is the most famous of the three laws because all of us have experienced some kind of pleasure or pain out of it at some stage in life. If you hit something like a rigid wall with a large amount of force with your hand, you will experience the pain from action-reaction principle because your hand will experience a reaction force, which will definitely cause discomfort. So the statement of Newton's third law is that every action creates an equal and opposite reaction. So this is the statement, okay. But again, we need to understand it in application point of view. So let's understand this from an example point of view. Now we'll start with a bit of an abstract example. We all know that charged particles apply force on each other, right? And that type of force is called Coulombic Force. You would have studied about it in atomic structure, for example, the Coulombic attraction on orbiting electrons from the nucleus. So let's take an example of Coulombic force between charged particles and how action-reaction principle works. So suppose we have one positively charged particle A and one negatively charged particle B. So we know that A will attract B with some force like this. So this we are labeling as the attraction force applied by A on B. Okay. But we also know from an experiment, which basically verifies Newton's second law, that while A attracts B, B will also be attracting A. And these will be along the same line, which is the center to center line of the two particles. So this one is now again an attraction force. But this is by B on A. Now it's an experimentally proven fact that the force applied by A on B is equal and opposite to the force applied by B on A. If this is the action by A on B, then this one is the reaction on B. Sorry, this was on B by A. Yeah, it's correct one. By A on B. So this is the reaction experienced by A because of B. This is the idea. So this is an example of the application of action-reaction principle in the case of charged particles applying Coulombic force on each other or applying force according to Coulomb's law. Now we'll see more examples also. Just make a brief note of this first of all. Sir, I have a doubt. Okay, now another aspect of forces that the concept of action reaction helps us understand is this whole business of normal reaction that we are talking about. Okay. Normal reaction force. Let's understand this in more detail. It's a type of force. So basically, what is normal reaction force? It is a contact force. It's a contact force between any two surfaces pressed against each other. Okay. And the direction of contact force is normal. Normal is another word in physics for perpendicular. So basically, how you hear the term normal, how you read it, is that it's a perpendicular direction force. So it's a reaction force which is in the perpendicular direction. So it's a normal or perpendicular to the plane of contact. So the most basic example of this is the one we just saw a while back, that you have an object kept on
A table, a
some kind
book
of
on a table.
any object like a block or a book or anything that's kept on a horizontal surface like a floor or a tabletop or whatever it be. Okay. So you have a block of mass m kept on a horizontal surface. Okay. So now we will understand the concept of normal reaction also by action reaction principle. So what is happening here is that the block will actually press the table downwards. because of its weight, the block presses the table or the surface down. Okay, so that net force with which it presses, that's called N. So when we think of the surface, it's experiencing a net force vertically downwards, normal contact force. Okay, this is on the surface, on the horizontal surface, applied by the block. Okay. And now if you think of the block's free body diagram, that in turn has the reaction to this one. So I'll just make the free body diagram of the block above. So now the table is applying this kind of contact force. Okay. So this and this, they are an action reaction pair. Okay. Because this is the vertically upwards force, but this is on the block, okay, applied by the table. You can see that this one is the normal reaction on the block by the surface. Okay, this is the normal reaction on the surface by the block. So it's in the downward direction. So they are equal and opposite to each other. So they are an action reaction pair. And then the other force acting on the block is its weight. Okay, and the block is at rest. So from that you can understand that net force on the block should be 0 because its acceleration is 0. So N minus mg should be 0. So this normal contact force has a magnitude equal to mg. So for example, if the mass of the block is 5 kg and g is 10 meters per second square, so that means this normal reaction has a magnitude of 50 newtons. But this normal reaction actually represents a pair of forces, an action reaction pair. The table will experience a vertically downward force of 50 newtons with which the block is pushing it. And the block will experience an equal and opposite reaction force upwards. This vertically upward force of 50 newtons magnitude. Okay. So whenever we have two surfaces which are pressing against each other, they apply an action reaction pair on each other. A pair of forces acts. A applies a force on B, B applies an equal and opposite force on A along that direction, which is along that axis which is perpendicular to the plane of contact. So here in this case you can see that the block's lower surface, okay, and the horizontal floor or surface or whatever, or we call it the tabletop. So they are two surfaces in contact. They are in contact such that the plane of contact is horizontal. So the contact force is in which direction? Vertical. It's horizontal. So therefore the normal reaction, that is vertical. Okay. So always remember, normal reaction is a contact force that acts in the direction which is perpendicular along an axis which is perpendicular to the plane of contact, and it always acts in a pair. Okay. On a single body, of course, there will be only one normal reaction, but whatever normal reaction that body is experiencing, that body will apply an equal and opposite reaction on the other surface it is in contact with. Okay, so now let's understand this concept of normal reaction with some more examples. So as you have actually already seen in the previous example, the normal reaction of an object on the ground on a horizontal surface need not always be equal to its weight. We had seen that example where the weight was 100 newtons and the normal force was only 70 newtons. It's always possible something like that happens. Okay. So let's look at this example next. Okay. So we're not applying any external forces and all that. Okay. It's just two simple blocks which are kept one on top of each other, and their masses are like this: 5 kg, 10 kg, and take the value of g as 10 meters per second square. So now we want to find the normal contact force between A and B, or the normal contact or reaction force. And same thing, now the normal reaction force between B and the flow. So this should be very easy. Quickly work it out. Okay. And send me the answers. Very good, Rishita, that's correct. Yes, very good. Both the answers are correct. Vidhi, I think you just added 1 0 by mistake. Just check. Yeah, it's correct now. Good. So we just need to make a force diagram for each of these blocks. What we'll basically understand later is a free body diagram for each of these blocks. So on A, you'll notice there are only two forces acting. There is its weight, which is 50 newtons. And there is, let's say, normal reaction N1, where N1 is the normal reaction between A and B at the surface of contact. And N2 is the normal reaction between B and the flow. So we'll come to that later. Now on B, you can see there is normal reaction that A is applying downward, equal and opposite, that is then its own weight, which is 100 newtons, and the normal reaction that the floor is applying on it, N2. Now both of these are at rest. The net force on them must be 0. So N1 must balance the weight of A. So the normal reaction between A and B, it has a magnitude of 15 newtons. That action reaction pair, which you can see here, it has a magnitude of 15 newtons. So B applies a normal reaction in the upward direction on A, and A applies an equal and opposite normal reaction on the downward direction on B. So now if you look at B's free body diagram or vector diagram, the net force on it is 0. So N2, okay, which is this force acting on it because of the ground, is balancing these two forces. So N2 has a magnitude of N1 plus weight of this. The normal reaction between the ground and this is this. So if now we ask that how much force is the ground experiencing, okay, that will be 150 newtons. So the floor experiences a downward direction normal force of 150 newtons applied by the block B. Even though the weight of the block B is less than 150, it's only 100 newtons. But the force that B is applying on the floor, that is 150 newtons, because B is also getting pressed down by A. Okay, so that is contributing to that normal reaction between the floor and B. So the floor is ultimately experiencing a downward pressing force of 150 newtons. Yes, madam, what's, sorry, I think your voice just got cut. What is the question? Okay, now let's see another case of interesting case of normal reaction force or normal contact force. This time we'll take this kind of a situation. There are two blocks which are against each other. This system is on a smooth horizontal surface. Now we are applying an external force horizontally on A like this. So A and B are blocks of mass 3 kg and 2 kg respectively. Kept in contact on a smooth floor. Now they are at rest initially. Now a constant horizontal force of magnitude 10 newtons is applied on A as shown. So we have to find acceleration of A and B, and we have to find all normal contact forces in the system, including between A and B, because they also have a surface in contact. Okay, so just try out this question, people will discuss further. Okay, very good. We will see that the acceleration, Sanvi, your answer is correct. The acceleration will be 2 meters per second square, and the contact force between the two blocks. So one thing we can understand straight away, which I hope is clear to all of you, is that they will have a common acceleration because they remain in contact. No? So acceleration of E is equal to acceleration of B, which will be this common value A. The horizontal acceleration. So now if we make the diagrams for A and B individually. So the moment you start pushing A with some external force, like this, now what happens is immediately A pushes B because it's against B with some normal contact force. So B has to push A back with an equal and opposite normal contact force. So this I'm writing as, suppose N, and write it as NAB also, whatever. So this one and this one here are an action reaction pair, this N. This is the contact force, the normal reaction. But between A and B, the two objects. But of course, there is also normal force that the ground is applying on each one. So they are like this. So they are NA and NB, suppose. And each of them has their own weight. And now, most importantly, they have the common acceleration. This is the horizontal acceleration A. So for block A, we have the horizontal equation that F minus N is the net force. So that should be equal to mass into acceleration. And for the vertical normal reaction that the ground is applying minus the weight should be 0. As for the block B, we have in the horizontal direction, we have N is equal to this equation. And for the vertical direction, this. And mass of A was 3 kilograms. Mass of B was 2 kilograms. Okay. So if I write equation 1, we have F minus N is equal to MA. And if I write equation 3 from here, N is equal to this. So we can solve these equations by just, for example, adding them. We'll get F is equal to this. So the acceleration is this much. The force we'd applied was 10 newtons. That's the first thing. Okay. Now substitute this in equation 3. So we get N is equal to 2 kg into 2 meters per second square. So the normal reaction force between the two blocks is 4 newtons. You can also substitute in equation 1. Okay, the same thing. Okay, this is clear, I hope. And there are two other contact forces, which are the normal reaction due to the grounds, which you can just see are equal to the weights. So from equation 2 and equation 4 above, you can see that this is equal to 30 newtons. And the normal reaction due to the ground on B is equal to its weight, so that's 20 newtons. So that completes all the variables which we've been asked in this problem. Okay, people, so hope this question is fully clear.
Yes, sir.
Yes, sir.
Okay, and you have also understood the concept of normal reaction as a contact force through these 2 or 3 examples. So we will conclude today's session here, and next session we'll see that another important force in Newton's laws problems becomes what we call tension or tensile force in anything like a thread or rope or chain or any flexible material like that which is being pulled. So in that also we will see application of Newton's third law and action reaction principle, and from there onwards we'll move ahead. Okay, so I will send you a small worksheet also, and meanwhile you can also get started from H.C. Verma. If you have that H.C. Verma part 1 Newton's laws chapter, you can go through the first 5 solved examples and also question number 1 to 8 in the exercise, in the main exercise of H.C. Verma Newton's laws chapter. Okay, and I'll be sending you worksheets which are different from the worksheets you might have seen earlier in, so you'll get some fresh problems to do. Yeah, module is more than enough. You can do module, it's more than enough along with the worksheets.
Sir, I have a doubt related to. Sir, if every action has an equal and opposite reaction, then how come anything move?
Because action and reaction, see, doesn't act on the same object, no? You understanding the point, no? So, for example, here the normal reaction acts on B. Okay, that acts only towards the right. No? The reaction which is acting on A towards the left, is it acting on B? No, no. On B only one of the two is active, either the action or the reaction. So the reaction will not cancel itself. You understand? No?
Okay, sir. Understood.
Okay, so that's also something important. Yeah.
I had a doubt. Like we had a force of 10 newtons, like
Yeah.
A block, and then we again had a N that's in the opposite direction with the same force, right? That's 10
No,
newtons.
not the same force, not the same force, because see, when F would be equal to N, only when the block is at rest. But see the free body diagram of A over here, the block A is not at rest, no? So obviously N is less than F. You understanding now, no?
But then we got the magnitude of N as 10, right?
No, we did not, better. See, no, the N is coming out to be 4 newtons below, see? Solved, no?
Oh, okay, so sorry, sir.
Understood, no? And that's why it's coming out to be less, no? Because block A is moving. Okay. If we
Okay,
had
sir.
kept the block A against a wall, then that would happen. Whatever force you're applying, the normal reaction would balance that because it would be at rest. So it would be 10 newtons. Okay. So hope this is clear, people. Sanvi, this point is clear now. Okay, okay, good. Yeah, and to answer your question, we'll just let you know how the backup classes for your calculus will happen. For those who have migrated from Purple House to this batch. Okay. Let me just work it out with Hemant sir and others, like how we are planning the backup classes for calculus. Don't worry. Okay. So that's it for today's session, people. Wish you all the best. Thanks for attending.
Thank you, sir. Bye, sir.
Thank you, sir. Bye.
Thank you, sir. Bye, sir.
Okay, bye.
Thank you, sir.